Okay, IR spectroscopy. Questions, comments, concerns. Hopefully you had a chance to watch the lecture. If you didn't, you should go back and do that because we're not gonna unfortunately, the snow day was the one day that we're doing a chapter just on that day. But I think it's pretty straightforward. Basically, there's those two charts, the one with the regular, the miscellaneous functional groups, and then a specific one with all the carbonyls. Both of those are going to be given to you on the exam. So you don't have to memorize those, you just have to know how to use them. All right. So next topic is stereoisomerism. So this is basically the 3D shapes of molecules, more so than we've already talked about, because we talked about Vesper theory and that sort of stuff, and that's going to come into play here a little bit. But first we need a reminder on the wedges and hashes notation for whether whether atoms are moving or are positioned coming toward you or going away from you. So if we have, let's say, a carbon and there's a wedge, and at the end of the wedge, on the thick end of the wedge is a hydrogen. That means the atom on the thick end is coming either towards you or out of the plane of the board or the screen. Okay, so maybe we could draw a nice big bold H there to show that it's coming towards you, I guess. And then the opposite is true for this dashed or hashed thing. Let me see if I can do that a little nicer looking. There we go. So the atom on the thick end of the hash is going away from you or going into the board. So we can maybe draw that as a tiny little hydrogen that's back going into the board. So it's really important that you kind of get familiar with this and maybe not immediately, but at some point be able to kind of recognize what this means instinctively without thinking about it. And that just will take some more practice to get to that point. And we'll have plenty of that to do. So if anybody brought their molecular modeling kit, which I should have sent out an announcement because I said it in the video, but if you didn't watch to the very end of the video, maybe you didn't hear it. But if you happen to have your molecular modeling kit, we'll go over that now. And in order to illustrate some of the wedge and dash notation, we're going to build ethane. So ethane is H3CCH3, 2-carbon chain. So generally speaking, your modeling kit is going to have whole bunch of atoms and a whole bunch of connectors. So usually black is carbon, red is oxygen, blue is nitrogen. I feel like those colors make sense to me. I don't know if they make sense to you, but maybe sulfur is yellow or something like that. And then you'll probably have some smaller balls, white or gray or something. Those are hydrogens. And then you'll have a selection of connectors. Usually you'll have some small ones that are kind of stiff and maybe long ones. You might have flexible ones. For today's purposes, we're really just going to use the carbon and hydrogen and maybe some others. If you've got, for example, this kit is a bit of a mess. Has hydrogens that are white and it's got some other small ones that are the same size that are various colors. Those can be convenient too. But as far as the connectors go, we'll just use all the same type of connector. So you'll notice on the carbon atom, it's tetrahedral, like sp3 carbon should be. It's got 4 equally spaced holes. And if you don't believe me, go ahead and put a connector into each one. And you should get a tetrahedron, which is sort of like a tripod kind of thing. Okay. So for ethane, we've got a carbon with 3 hydrogens, the CH3 group. Okay, so you can make that. And you don't technically have to put on the hydrogens. You can just leave the ends blank and know in your mind that that's hydrogen, but you do know the purposes, I'll build it explicitly. Okay, so a CH3 group, there's your methyl group. Good. And ethane is a methyl group connected to another methyl group, right? So carbon-carbon bond, there's our carbon-carbon bond in the middle there. And then 3 hydrogens. Okay. Okay, cool. So one thing, and this is kind of getting ahead of ourselves, but just so we can draw a good looking diagram. So if you look at right, if you look at the molecule from the side and then turn it so you're looking at it head on, so you can only see one of the carbon atoms. You'll notice the way I've got it set up right now, if I hold it so you can see, the one of the CH3 groups is right on top of the other one. So the hydrogens are behind the other hydrogens. That's called eclipsed, okay, because it's like an eclipse. You can only see 3 hydrogen atoms and the other 3 are behind. Okay. What we want is we want to turn it so that the front hydrogens that are closer to you are within the gaps between the rear hydrogens. Right, so you should be able to see all 6 kind of in a star pattern, an asterisk like this. Okay, that's called staggered. We'll talk about staggered and eclipse in a second. But when you build ethane like this, we want it to be in a staggered form. Okay, so that's how we're going to draw it with our wedges and dashes. And so, you know, typically we draw hydrocarbons, larger hydrocarbons, in a zigzag pattern, kind of like that. That's butane, the way I've drawn it there. But let's say that these 2 carbons are our ethane carbons, okay? And those are going to be CH3 groups, okay? So what I'll do is look at my ethane molecule from the side, and I'm going to say that instead of methyl groups in butane, those are hydrogen atoms. So we'll make this ethane as we have it here, okay? So now we have no wedges and dashes in our structure. So that means that all of the 4 atoms that we've drawn explicitly so far are in the plane of the board, okay? So that means that it should be oriented like I've got it here. So our two carbons are in the plane of the board, if you can imagine it, slicing through the molecule like this. And then on the bottom left, pointing downward, is a hydrogen. And on the top right, pointing up, there's another hydrogen. Okay, so those are the four atoms that are in the plane of the board. And now we've got to deal with the other four hydrogens that are going to be on wedges and dashes because they're coming away from and toward us. Okay, so on the leftmost carbon, both pointing upwards, right? The way I'm holding it here, both of these hydrogens are pointing upwards. One of them's coming toward us, and one of them's going away from us. So that means on our drawing, we're going to have a wedge with a hydrogen on it going up. So that's this hydrogen. It's coming towards us. Okay, and then we've got one that almost looks like it's right next to it if you're looking from your perspective. Okay, it's also pointing upward. And it's going back. So it's going to be on a hash. Right? Okay, same goes for the carbon on the right. We've got the hydrogen we've already drawn in the plane of the board. That's going upward. And then we've got two hydrogens. These are going down. One of them's coming toward us. One of them's going away from us. Okay, so can draw in one going down on a wedge and the other going down on a hash. Now, it doesn't matter if you put the wedge on the right and the hash on the left. You can flip those around or do whatever, because it kind of depends at exactly, what angle you're looking at the two front and back hydrogens on a specific carbon, and it didn't really matter. So that is our wedge and dash skeletal structure of ethane based on that molecular model. All right. So I talked about the eclipsed and the staggered kind of thing. Notice that your physical model, right, rotates, okay? Depending on how broken in your bonds are. You can rotate around this carbon-carbon central bond, okay? You can also rotate around the carbon-hydrogen bonds, okay? You can twist the hydrogen. Now, obviously, this doesn't do anything interesting because you're just rotating the circle around. So we don't really care about the fact that you can rotate around the carbon-hydrogen single bonds, but the carbon-carbon single bonds, we can do this sort of propeller thing. And so we can, make any arrangement of, right, we can have this eclipsed kind of thing. We can have this staggered sort of thing. We could have it halfway in between. And then on top of that, in this case, all six hydrogens are the same. They're all hydrogens. But if we replace one or two of them with different substituents, different groups, now we have, sort of an infinite number of different possibilities that we can make. So those positions that we can put the molecule into, we call those conformations. And the different molecules that result from putting a compound in different conformations are conformers, right? So our skeletal structure with the wedges and dashes doesn't really do a great job of showing conformations, right? Because as I've been demonstrating this to you, I've been looking at it where, we're looking straight down the carbon-carbon bond. So it'd be really nice if we had some way to draw from this perspective. Spoiler alert, there is. And they are called Newman projections. I assume there's a dude called Newman. I don't know what his importance was, but so these Newman projections are almost exclusively used in order to look at different conformations, because in in an application where you don't care about the 3D shape of the molecule, well, drawing a Newman projection is going to be too much work. So before we get to the actual projection, we'll kind of step our way there. So we started with a skeletal structure with wedges and dashes. And what we want to eventually get to is something where we're looking head on right down the CC bond. Okay. So let's got it like this. Let's take the molecule to side view, right? This is a side view, essentially, the molecule. And let's slowly rotate it 90 degrees. And we're kind of going to draw like as a head-on view kind of thing. And this is not a real thing. This head-on view. But it's really halfway between what we drew up there and a Newman projection. So we could say that, all right, nope, color. Sorry. Okay, so this is going to be the front carbon, okay? And the front carbon, we're looking at it directly head on, has three things attached to it. There's something else at the back, but we'll get there in a second. Three things attached to it, all in a triangle. They're actually coming toward us, but whatever. Three things attached to it in a triangle. Those are all hydrogens. Okay. And this is going to be, no, don't do that, please. That's going to be our carbon-carbon bond going backwards. So I suppose really we should make it into a wedge, kind of an ugly wedge, but okay, so it's a wedge showing that the front carbon is coming toward us, I guess. Okay, at the back, we have a carbon, that be yellow, and it has the same triangle pattern just upside down, at least in this staggered configuration. Okay, so we have something like this. I'll draw it a little smaller to show that it's further away. And those three substituents are all hydrogens. Do we see how that represents the same thing in 3D? Okay. So we're all cool. So we're almost to the Newman projection. Really, all we're going to do is, rather than have these two carbons be offset, we're just going to smack them on top of each other. All right. So the front carbon is going to look just the same. You can draw a dot in the middle if you like, but it's not required. And then, okay, so I've just said that we're going to put it's like this. We're going to put them directly on top of each other, okay? So that means that this carbon-carbon bond is completely invisible, all right? So, and additionally, from that perspective, the back carbon should be completely invisible, right? So how does that work? So there's, actually, let me draw it first, then label it. So the back carbon is actually going to be a circle, okay? So the front carbon is a dot. Get rid of this. And back carbon, circle. Okay, so here's our head-on projection. And this is the Newman projection. So looking like this. Okay, notice a couple things about the way I've drawn the Newman projection. Okay, the blue front carbon, those bonds go all the way to the center and they intersect just like a normal skeletal structure would. But it's very important that the back carbon in yellow, that these lines only go to the circle and then stop. Okay, what you don't want to do, and I'm going to do it, what you don't want to do is end up with this kind of thing. Okay, where you've got 6 lines all intersecting in the middle. This peace sign thing, don't do that. No peace. Okay. Because so if you're doing it in color, it's less it's less confusing. But if I do that, all of a sudden it becomes really important that you don't draw those lines inside the circle. Okay. Okay, so let's do this molecule. What I would recommend is that you build this. If you don't have your kit, get with somebody who does have a kit. Actually, that'll have to do, I guess. So we're going to draw a Newman projection of this molecule. And in order to show, in this structure, we need to have a way to specify which way we're looking in the Newman projection. In ethane, it was pretty easy. But in this case, I'm going to say that I want to look down that bond like that. And so I'm going to draw a little eyeball. There we go. Lashes and everything. A little eyeball looking down that bond. Okay. So that means that our Newman projection is going to be viewed from up here, looking that way. All right. So let's build that. So this is 2,3-dibromobutane. Okay. What you'll need to do, kind of the short version of this, is each of the carbons needs to lose 2 hydrogens. We need to replace with a methyl group. And for a methyl group, rather than putting on a carbon and then 3 hydrogens, I'm just going to put the carbon on, because we don't really care about the 3 hydrogens on this carbon or on that carbon, because we're really only concerned with this CC bond. Okay. So let's see. Done it correctly? Yes, I have. Good. So the 4 carbons are all in the plane of the board. All right. We have 2 bromines, and they're both coming for us. So I'm going to use these little red ones for the bromines, but use whatever you like. Okay. One of the bromines looks like it's going up, kind of, and coming toward us. The one on the left carbon. The other one looks like it's going down and toward us. That's on the right carbon. Right. Now, by process of elimination, what has to be on the back sides of those two central carbons? Hydrogen. Yeah, we got to have hydrogens there. Okay, so we can draw those in on our skeletal structure. So these we said were methyl groups or CH3 groups. Got a bromine coming forward and a hydrogen going back. Now, if you randomly put on a carbon, a hydrogen, and a bromine on both of your central carbons, there's a 50-50 chance that you actually won't get this molecule. You'll get one where you feel that. Where the bromine and, right, in this case, the bromine now, there's one on the front and one on the back. You try and turn it so that both of the bromines on the front are on the front. Uh-oh, all of a sudden, now the methyl groups are on the same side rather than being in a zigzag. Okay, so make sure you've got that correct. That's actually what stereochemistry is. And we'll get to those two different kinds of molecules probably next time. Okay. So you should be able to build that model. And now, okay, we're looking for a Newman projection looking that way. So looking that way. So all we got to do is take our molecule and rotate it so you're looking at it like this. Okay. Now you can see though that six-membered asterisk star looking thing, and that's the Newman projection that we're going to draw. This is why you're allowed to have the modeling kit on the exam. Okay. So we need the basis for our Newman projection, which is going to be not this way, but actually what we're seeing is this. So on the front carbon, the methyl group is going directly down. Okay. So blue is front, yellow is rear. Okay, so coming directly down is a methyl group, right? Going up and to the left on the front carbon is a hydrogen. Going up, yes, your left. My right, your left. Okay, going up and to the right on the front carbon is a bromine. So there's the front. On the back, going straight up is a methyl group. Going down and to the left is a hydrogen. And going down and to the right is the other bromine. Pass this around to folks. So something else we should note here, and this is kind of a way to check your work, is on the skeletal structure. Both of the bromines are on the same side of the molecule. They're both coming toward us. And guess what? Look at the Newman projection. Two bromines are also on both sides of the molecule. Okay, so if you see two things on a wedge right next to each other in the skeletal structure, and you draw a Newman projection and suddenly they're 10 miles away from each other, that should be a red flag that maybe you need to check either your physical model or the model you've made in your head and make sure you've got the right orientation of things. Another thing I would recommend is, if possible, do this kind of three-step process where you start with a regular skeletal structure and then you build out this more explicit skeletal structure where you've got wedges and dashes on each of the two carbons that are of interest to us. The ones in the CC bond that we're looking down. And then from there, go to the Newman projection. If you try and do this, which eventually you should be able to do, just go directly from the naked skeletal structure, you're liable potentially to forget the positions of hydrogens mainly. Hopefully you could recognize that the methyl group is the carbons on the ends, but the hydrogens in particular hide from you because they're typically not drawn in skeletal structures. Questions on drawing Newman projections?
Are you going to give us that very first thing that said both the bromians were pulled forward? Or am I supposed to know that both of those bromians are big?
Yeah, so what tells you that they're coming forward is the fact that they're on wedges.
But you're going to give us the wedges.
Yes. Yeah. Oh, as opposed to me drawing that just with lines. That's ambiguous, and you could draw a couple different Newman projections that would be correct there. But if I was just asking you to draw one, then yeah, I'll give you the wedges and dashes. Okay. So, speaking of that, we have nope. Yeah, so we looked at the Newman projection just like this, right? But who says that the molecule isn't rotated like this? Or like this? Or that the back one hasn't rotated, right? We can rotate around this carbon-carbon bond. And there's one specific conformation that we've drawn here, but there's other conformations that are possible. And so looking at that is called conformational analysis. So recall the free rotation and in this case, we're talking about single bonds. If we've got a double bond going on somewhere, those don't have free rotation. And in fact, a little side note, we won't do this for this particular exam, but if you've got the long bendy pieces, you can actually make a double bond by starting with a single bond and then adding another one, attaching the two carbons, and now you have, right, this is almost like the two lines of the double bond. You'll notice that you can't, if we, instead of getting on this for another kind of topic, but so get to show all the stuff about the tips. This is fine. So if we have a double bond and then we've got hydrogen on the outside, you can't bend this. I mean, you can, but you're gonna break it. You can't rotate here. So this molecule is locked in place. This is one of the areas where the kit is fantastic because the physical model prevents you from doing something wrong, like trying to rotate around a carbon-carbon double bond. But if we just have a single bond, like so, we can rotate free. Anyway, so we have free rotation around single bonds. So let's not use that more complex bromobutane example. Let's go back to just ethane. So we'll draw Newman projection of ethane like this. So we know that the blue front carbons are closer to us and the yellow back carbons are further away from us. But if we sort of flatten everything down and look at it in 2 dimensions, the angle between two of these neighboring hydrogens, again, they're not neighboring because they're on separate carbons. The angle here, I haven't drawn it particularly nicely looking, but this is a 60-degree angle, and we call this the dihedral angle. And this pattern where we've got sort of alternating blue and yellow as we go around in a circle, where they are staggered, is called staggered conformation. There's another option, which we also discussed with the models. No, I did it wrong. See, I drew staggered again, which is a good habit to get into, but that's not what I wanted. The other option is where one of the back carbon is hidden almost exactly behind the front carbon. That's called eclipsed. The way we draw it, of course, it would be kind of impractical to draw them directly on top of each other. So we just make it as close as we can. But I think we can still see from this diagram that they're pancaked right on top of each other. So now the angle between 2 hydrogen atoms here, if it was drawn perfectly, this would be a 0-degree dihedral angle. And as I said, this is called eclipsed. Okay, so if we look at these 2 carbons as substituents on the top here, if they're eclipsed, there's this, a certain distance between the 2 carbon atoms, like this distance. If we stagger, like so, that distance is a little bit longer, right? Because we've just moved it to the side a little bit. Okay. And so in a staggered conformation, there's a little bit more distance between all of the substituents, and I think that's seen very clearly in the Newman projections. And so because of that, the staggered conformation is lower in energy than the eclipsed conformation. In fact, in ethane, if you just take a picture of a sample of ethane, almost all of the molecules will be staggered and 1% will be eclipsed. Now, because there's free rotation, right, it's not that 99% of the molecules are locked in staggered configuration and 1% of them are locked in eclipsed configuration. They can rotate freely, but generally they come to rest in a staggered position. Okay, that is relatively simple to digest when all of the substituents are hydrogens, right? There's only 2 options. They can be staggered just like this, or eclipsed, just like that. But if we look at a molecule like butane, projections. Now we have more substituents on our two carbons of interest, which we'll keep the same ones here. More substituents than just hydrogen. So we can do the same process that we did with the dibromobutane example from up here. We want to go from this first molecule that's just the skeletal structure to a slightly more expanded molecule that has all of the wedges and dashes on it. In this case, we don't have any wedges and dashes. Okay. Ugh. No. There. Okay. So we make our zigzag shape with 4 carbon atoms, like that is what we're looking at in the skeletal structure. So our 4 carbon atoms are in the plane of the board. They don't have wedges or dashes. And so all we need to do is fill in these 2 hydrogens on the left carbon, both of them pointing up, one of them coming towards you, one of them going away from you, and the 2 hydrogens on the right carbon. Well, of the 2 carbons we're most interested in, so we've got those methyl groups, whatever, we're looking right there. So on the left carbon, we have a hydrogen coming toward us and a hydrogen going away from us that are almost on top of each other. And then on the right carbon going down, one of them coming toward us and one of them going away from us. I don't want to do it the other way again, don't I? Okay, so again, we're going to look at it from the left-hand side of the molecule. So going down from that perspective, on the front carbon is a methyl group. On a wedge coming toward us on that carbon is a hydrogen. So in the new in projection, when we're looking at it from the left, that front carbon is going to be on the upper right. So that's going to be there. And going backwards, in this case, to the left is another hydrogen. Okay, so that's that carbon there. The back carbon will be this one. Going straight up is a methyl group. And then coming down both toward us on the right and away from us on the left are hydrogens. Do we see how I got to that point? So it doesn't feel natural to you, playing with the models, I think will get you there. more quickly. All right. So we talked about staggered and eclipsed from above, and I didn't even tell you to do staggered, and we just did staggered because that's how the molecules are usually drawn, because that's how they usually are. So this projection here is staggered, but there's more we can do to describe it, right? Because of the methyl groups. So in fact, let's go ahead and take the front carbon, the blue carbon, and rotate it clockwise 120 degrees. So that's not going to change the lines. We're still going to have the same Newman projection. Oh my God. The Newman projection shape like that. The back carbon is going to stay the same. Okay, and now we're deviating from the way we've drawn it in the skeletal structure. So don't try and compare those two directly. Okay, the front carbon has been rotated clockwise by 120 degrees. So that means the methyl group is going to move from the south to the northwest. And then those two hydrogens going to move clockwise. So we've got a hydrogen here and a hydrogen here. So is this structure staggered or eclipsed? Yeah, still staggered. But it's different in that the methyl groups are far apart on the left and close together on the right. Okay, so when they are far apart, we call that anti-configuration of methyl groups or ethyl groups or whatever things, just things other than hydrogen. And then in the structure on the right, where the two methyl groups are closer to each other in rotational space, that's called gauche. Okay, so here we're just talking about the methyl groups. So those are our two staggered options. We can also do some more playing with rotation to make two different eclipsed conformers. Okay, so I want to do it like this. Yeah, fine, I'll do it like this. We could have this set up here. So this is eclipsed. And the way I've drawn it here, both of the methyl groups are right next to each other. So we have methyl-methyl interactions. Right, those two methyl groups are repelling each other. The hydrogens are too, but more importantly, the methyl groups are not happy being right on top of each other. So we can do the same transformation here. Rotate the front carbon clockwise or counterclockwise, or rotate the back carbon. It really doesn't matter at all what rotation you do. You just have to do something to it. No, I drew, see, look at me. Drew staggered again. Okay, so the back carbon here will stay the same. Hydrogen here, methyl here. But now the front carbon has been rotated clockwise 120 degrees. So the methyl is now over here. And the other two are hydrogens. This is also an eclipsed conformation, but here we have interactions between the methyl groups and hydrogens. So this methyl group is interacting with this hydrogen, this methyl group with this hydrogen. Those are our four possible conformations of butane. Which of these do you think is the least stable or the highest in energy?
The eclipse, methane.
Yep. Yeah, so it's going to be this guy. Because, well, the eclipsed, first of all, we know that eclipsed is less stable than staggered, higher energy than staggered. And then we've got these two big groups, the two biggest groups in the molecule crashing into each other. That's unfavorable, that's higher energy. What about the lowest energy or the most stable? Yep, the staggered anti. Because the two methyl groups are as far apart as they can possibly be. And the entire thing is staggered. So not only are the methyl groups happy being far apart, but all the hydrogens are fairly far apart, more so than they are in the eclipsed structures. It's much less important, but which of the other two is lower in energy, do you think? Gauche or eclipsed? Lower in energy, more stable.
This one was sort of the same distance away, I would probably say the staggered is more stable because the hydrogen are farther apart.
Yep. So it's a very good observation. The methyl groups are the same distance apart, 60 degrees. So that doesn't matter. What does matter is that the hydrogens in the eclipsed are crashing into things, and in the gauche they're not. So this is the second lowest energy. And this is the third. Again, this is not nearly as important as the staggered anti being the most stable. That's sort of the key here. So the big takeaway is, well, staggered is always going to be lower in energy than eclipsed. I think we already talked about that, but this proves it maybe even more. So that means it's actually gonna cut down on some work for us. For example, if we're asked for the lowest energy conformation of this molecule, and for simplicity, I'll specify the direction that I'm going to look at in the Newman projection. Okay. So I'm going to cheat and skip the process of drawing out all of the wedges and dashes. And tell you that that is the Newman projection for that perspective of that conformation of that molecule as I've drawn it. It may or may not be the lowest energy conformation, but what we want to do is figure out if that's true or not. So staggered only, because staggered is going to be lower in energy than eclipsed, so we don't have to worry about eclipsed. So what I'll do in this case is, you'll notice there's on the back carbon, it's got 2 hydrogens and 1 substituent. Okay, so in this case, it would be a good idea to focus on the interactions of that substituent, in this case, the ethyl group, because we can rotate this more complex front carbon around it, and we just have to look at that ethyl group on the bottom and the 2 things that are next to it. So what I'm going to do is do 2 rotations, right? We've got 3 positions on each carbon. And so we need to make all 3 conformations that are possible here. We're going to hold the back carbon the same. With that ethyl group that we're going to use as sort of our control. And so, like we did in the previous examples, we're going to take the front carbon in blue and rotate it 1 turn each time. So one way we can do that is say, all right, the ethyl group is going to move clockwise 1 position here, and then in the next molecule, it moves clockwise another position. The methyl group is going to move clockwise 1 position to there, and then again clockwise another position up to the top. Hydrogen is the last one. It moves clockwise 1 position and clockwise another position. So we're going to keep track of one group, in this case, that ethyl group, and examine what its neighbors do and its interactions with its neighbors as the molecule rotates around.
Wait, but when both ethylene be too close to each other, will that have a lot of energy or no?
Where specifically are you talking about?
Last stage.
On the third one?
Yes,
Yes.
but trying to those energy configurations.
Yes, we are.
And so with methyl being farther, make lower energy.
Yeah.
Okay.
So we are on the first example, we have the ethyl group next to a hydrogen and a methyl group. On
And
this,
so we want to get that far away as possible, and then everything else will just be lower energy, right?
yeah, pretty much. So in this case, we have it next to a methyl group and an ethyl group. And then in the last example, an ethyl group and a hydrogen are neighbors. So there's one that we can eliminate pretty quickly. And what is that? 1, 2, or 3? 2. Yep. It's got 2 hydrocarbon groups next to the big hydrocarbon group. So, right, you can even see that as all the 3 hydrogens together at the top and the 3 alpha groups together at the bottom. No bueno. Okay, what about between 1 and 3? Which one is lower in energy, more stable?
Most negotiating the stable about, because we may not want the right single stable, and therefore if we want the second stable, it would probably have to be.
So in the first one, we've got a hydrogen and a methyl group as neighbors, right? A methyl group is 1 carbon, CH3. An ethyl group here is larger, CH2, CH3. And so this has more stuff next to the ethyl group. The blue ethyl group is larger than the blue methyl group. And so this one is the lowest energy and the most stable. It's not a coincidence that in this molecule, the ethyl groups are anti to each other. I would say be careful with that. You shouldn't assume just because the 2 largest groups are anti to each other means that is the most stable. You have to look at all the neighbors of one of the groups. But it is a hint to that effect. No. Yes. Questions on conformational analysis? All right, awesome. Next time we'll start talking about conformations of cyclohexane.